kind of things you did. Well, it's relevant, but for beginners, it's okay. And in terms of regularity for this equation, I'm not going to do that, but I want to mention. So regularity for first order Hamilton-Jacobi equation, you saw yesterday, and you're going to see that the most we can hope for is Lipschitz regularity. For second order equation, the general case is kind of still sort of open or something like that. But if we have the case of uniform ellipticity, and if H is convex or concave in the Hessian variable, then there is a famous theorem called Evans-Krylov theorems. That says that the solution is C2 alpha. So we have classical solution. This is not easy. By Evans and Krylov. And they use a very famous result by Krylov-Safonov. Yeah. They use the famous result of Krylov and Safonov theorem to prove that Evans-Krylov theorem. But they need to assume that this is convex concave in d square mu, and I think it in particular it applies for the Monchamp equation, determinant of d square mu to the f applied for Monchamp. This is highly phoned in I'm not. I don't know. You can ask that for more. Whatever. So that's the thing, and then I'm not gonna do this, but this is kind of fun. Maybe I can do that later on. Few years.
You can remind me what is
ellipticity. Okay, ellipticity means in general sense. Okay. Ellipticity means that if you differentiate in the Hessian slot, okay, let's say x, d square of x, h is, so, okay, this is not a good variable. H, x, p, and okay, 1. Yeah, okay, and it is, sorry. D square of y of h is going to be between minus alpha times the identity and between minus 1 over alpha times the identity. There's a matrix between that for some alpha greater than 0. And then if you want to grid this, yeah, there's a book by Caffarelli Carver, but you know, there's also a lot of other results, but let's just kind of review on the literature. Okay, so what I'm going to do today is that I need to do a little bit more about, after I use existence uniqueness, I need to do a little bit more about stability. This is easy, it's easy. But let me state anyway the theorem. So let's say, assume that UK is a sequence in CRN, continuous functions, and HK is a sequence continuous function in CRN times Rn. And I have the following, and I have HK XP converge to HXP locally uniformly, and I have UK converge to U locally uniformly for some U in CRN for example, H is C, Rn times Rn. And UK is a viscosity solution. UK plus H of HK of X dUK equal to 0 in Rn. Then I can conclude that the limit is also a viscosity solution, the limiting equation. U is a viscosity solution of U plus H of X du equal to 0. Okay, again, this is easy to prove. Actually, this is U case, is unique, is the viscosity solution. U is also the viscosity solution. Okay, sketch proof. It's the same thing like one of the techniques we used yesterday. So if take phi in C1 Rn and U minus 3 as a strict local maxima at x0. So here's my U at x0. I take the test function, phi. Then because UK converges to U, so you know, of the axis, a subsequence Kj goes to infinity such that I have UKJ minus phi as a local max at a nearby point as xj. And I have xj converges to x0 as j goes to infinity. You know, it's kind of eccentric. This is kind of saying that it really says that we do have stability of.
Does AJ converge to infinity or 0?
J.
AJ converge to 0.
Oh, you know, it depends. Okay, sorry. Okay, here I'm going to take k in n, so it's conversion. So it's not epsilon, I guess. It's just way too far. Yeah. But if I do u epsilon, I just this is an epsilon conversion. So I have that, and then you know. This is really saying that in terms of viscosity solution, it relies on a small analysis fact saying that if I perturb the function u a little bit by some u kj, the local maxima is kind of stable. Right? It's kind of at a nearby point converges to the correct one. So it's stability of local maxima minima implies stability of viscosity solution. So with this, UKJ is a viscosity solution, hence it's a viscosity subsolution. I have this, so I have phi is a test function, so I have UKJ as xj plus h xj d phi xj less than equal to 0. So now I have j goes to infinity. Okay, and I end up with this one. When I let j goes to infinity, this one gonna go to u. Sorry. H. Yeah, x. Kj. Thank you. Yeah. So when I let j go to infinity, this one just converts to u x0 plus h of x0, the phi of x0, and then the other way around for solution. So I'm done. So it's kind of simple. Stability is simple. It already comes from the ideas of doing this kind of two function. Okay. So now I want to do one more thing because, you know, we have been talking about that this one can be only continuous, and it's kind of weird that, maybe this symbolic equation doesn't make sense at all. So I want to do some kind of consistency test because it should make some sense. So now I'm going to do some consistency. Consistency result. And then part of the result will be proved tomorrow, but this is a zero. So if U is a Lipschitz function in Rn, and is a viscosity solution of U plus H x du equal to 0 in Rn. Okay, remember that here I assume that it's a Lipschitz function. Okay. That's going to be checked tomorrow. So tomorrow I'm going to give you a set of tools that are available in the literature. I'm going to tell you the limitation and the needs of having new tools, the needs of doing new things, and the current trend, and then some new results in the last 5 or 6 years of this new study. But this is easy. U is a Lipschitz function. This is easy to do. So if U is a Lipschitz function, then by Rademacher theorem, we know that U is differentiable almost everywhere. And if it's a viscosity solution of this, then U is a solution of, I don't know my technique for this one, static, of S in the sense, in the almost everywhere sense. So yes, viscosity solution is also a solution in the almost everywhere sense. Then it makes sense, right? It makes sense to write this one down. So again, so that means